insulated gate bipolar transistor, that is IGBT. Figure A shows the structure of insulated gate bipolar transistor. Figure B and C shows equivalent circuit diagram and symbol. The insulated gate bipolar transistor is a new power switching device that combines power MOSFET and bipolar technology to provide the circuit designers with a device that has power MOSFET input characteristics and bipolar transistor output characteristics. So, IGBT is a combination of MOSFET and bipolar transistor. So, at the input, we get the characteristics of MOSFET, and at the output, we get the characteristics of BJT. IGBT is basically hybrid MOS gate turn on or turn off bipolar transistor that combines the function of MOSFET, BJT, and thyristors. IGBT is basically turn off power semiconductor device whose electrical characteristics approach that of ideal switch. Now we'll study the operating characteristics of IGBT. Before going with the characteristics, we'll first study the architecture of IGBT. So the architecture of IGBT is similar to that of MOSFET, except N plus layer at the drain is substituted by P plus layer at the collector. So in a figure we see that the N plus layer at the drain side is substituted by P plus layer at the collector. So the IGBT has three terminals: gate, emitter, collector. So at the collector side, the P plus layer is substituted instead of N plus layer of that of MOSFET. P plus substrate, N epitaxial drift region and P region form PNP transistors, whereas N epitaxial drift region, P region and N plus region form NPN transistor. So we can say that we have two combination of transistors, that is PNP transistor and NPN transistor, depending upon the substrate used. These two PNP and NPN transistor form parasitic thyristors. Once the conduction is started in forward direction, that is collector to emitter, the thyristors get latched. Latching is nothing but it gets locked into a conduction mode and the gate loses control over the conduction, which is not desirable. So in order to overcome such problems, a parasitic NPN transistor is prevented by properly controlling the resistance of P region and shorting the P-N plus region by emitter terminals. Now this is the static VI characteristics of IGBT. So in reverse characteristics and forward bias characteristics. So it is a combination of characteristics of MOSFET and BJT. So the characteristics of IGBT can be studied in following ways. First, forward characteristics. When collector is positive with respect to emitter and gate is kept open, the junction J1 becomes reverse bias and the device doesn't conduct and operates in forward blocking mode. However, if positive gate to emitter voltage, that is VGE, is applied, then the positive gate attracts electrons from the p region and induce n channel into the p region. Now, if this gate to emitter voltage, that is VGE, is less than threshold voltage, that is denoted by VT, then n channel is not sufficient to start the conduction. But when VGE equals the threshold voltage, the forward conduction starts. So we can say that when the voltage or a gate to emitter voltage is less than the threshold voltage, the forward conduction cannot be started. But the condition for starting the forward conduction is at when VGE, that is gate to emitter voltage, becomes nearly equal to threshold voltage. For the voltage, that is VGE greater than threshold voltage VT, due to n channel, the part of p region loses its identity as p region behaves as n region. Thus, the current flows from collector to emitter, and that current is called as forward current. The positive gate voltage determines attracted electrons and hence n channel width. So greater the voltage, or great, we can say that greater the gate emitter voltage, greater will be the flow of, or the high will be the flow of current. If the flow of current magnitude is very high, the electrons will be attracted more, and if the electrons are attracted more, there will be a change in the width of n channel. So n channel width determines maximum forward current. The transfer characteristics of IGBT is a plot of collector current, that is IC, versus gate emitter voltage VGE. When VGE is less than VT, that is gate emitter voltage is less than threshold voltage VT, the device is in off state, and for VGE greater than VT, device is in on state. So in order to start the IGBT in forward conduction mode, your gate to emitter voltage should be greater than the threshold voltage. Then and then only IGBT will be in on state. Otherwise, it will remain in off state. During this forward conduction state, if the collector voltage VCE is increased, forward current increases and finally reaches to maximum value limited by the gate voltage. Second, reverse characteristic. When negative bias is applied to collector with respect to emitter, junction J2 becomes reverse bias and device doesn't conduct. Thus, this provides device its reverse blocking capability. So when we apply a negative voltage to collector with respect to emitter, that is when VCE is negative, then junction J2 becomes reverse bias, and when junction J2 becomes reverse bias, the device is in off state, and when it is in off state, the current does not flow. Thus, this negative voltage blocks the flow of current. Hence, it is the ability of the semiconductor device to block the current. It is called as reverse blocking capability. If the reverse voltage is increased at a particular value, that is BVCER, that is called as break over voltage, it breaks down the junction J2.